Hello everyone, this video is part 1 of Econometrics, where we'll cover the motivation and basic setup regarding simple linear regression. I'm going to assume that you have completed calculus, and for other videos later on, you should have also completed introductory level course on probability and statistics. Let's suppose we have y and x, and that y depends only on x. So we have two variables, y and x, and we're going to assume that y is only affected by x. As an example, we'll let y be some exam scores of students in 2025, and we're going to assume that exam scores depend only on one x variable, which is going to be the number of hours studied. In econometrics, y is called a dependent variable, and the x variables are referred to as the regressors. What we're going to do is we're going to figure out how exactly y depends on x, or how exam scores are affected by hours studied. And the main statistical tool used in econometrics is called linear regression. It's simple linear regression when there is only one regressor, like our example here. Of course, exam score most likely depends on variables in addition to hours studied. But for now, we'll just consider y and x since this video is about simple linear regression. So then now we first want to take a look at the data. Before moving on, I just want to emphasize that the data that I use in this video is not a real data of y and x. I simply made the data up for this video. Okay, so then this is what our data looks like. As an example, the first student, student number 1, got 0.65 out of 1 for the exam score, and the student spent 3 hours studying for the exam. The last student, student number 30, got 0.77 out of 1 for the exam score and spent 4.8 hours studying for the exam. So as you can see, the data that I created for this video is a small one. There are only 30 students, and so we only have 30 observations or data points in our data. Okay, let's check how this data looks like on a graph. Exam scores on the y-axis and hours studied is on the x-axis. We have 30 data points on the graph here because we only have 30 students. So how would you interpret this data or graph? Well, as you can see, there appears to be a positive relationship between exam scores and hours studied. It looks like higher scores were achieved if you put in more hours for the exam. But of course, if possible, we want to be more precise than just saying that there looks to be a positive relationship. What if we simply connect all the dots from left to right like this in order to interpret the data? Well, it turns out that using this method for interpretation is not practical because there are too many ups and downs. For instance, one interpretation would be that if a student studies slightly more than 2 hours, score will actually be lower than just spending 2 hours. But if the student continues to study up until the 4-hour mark, then score is predicted to go right back up. For this particular data, that's exactly what's going on. But most likely you won't see the same pattern for other students in different samples or data. How about we just use a straight line to follow the overall trend in the data, like this. This way, using the slope of the line, we can make statements such as each additional hour of studying increases exam score by a slope of the red line points. In other words, using the line, we can make quantitative statements about the effect of hours of studying on exam scores. And not only that, compared to this type of analysis, interpretation using a line like this can be more generalized to different data or samples with different students, as long as you are correct to assume that relationship between y and x follows a line in general. So the main point that I'm trying to make here is that in econometrics, if you believe that the relationship between y and x is linear, then you use a straight line to fit the data, just like how we're using the red line in this page to fit the data. What if you believe that the relationship between y and x is not linear? Do we always have to use a straight line to fit the data? Of course not. Econometrics can handle nonlinear relationship between y and x. But that's for later stages. For now, we'll focus on the most simple case where we work with y and only one x variable, and we're going to assume that the relationship between y and x is linear. Okay, now then we have to figure out how exactly do we use a straight line to fit the data. Because as you can imagine, this line also looks to be a good fit to the data, and this one as well. In econometrics, the general goal is to fit a line through the data points such that the vertical distances between the data points and the fitted line is as close to zero as possible. So we're going to find this line, and this fitted line is going to be different than the red line that you're seeing on this page right now. And that's because the red line I simply drew on the graph without doing any calculation. So again, the goal is to find the line that somehow minimizes the overall distance between the data points and the line that we're trying to find. As an example, if we focus on this particular data point, we want to somehow get this vertical distance as close to zero as possible. And at the same time, we also want to get this distance close to zero, and this one as well, and so on. So ultimately, we want to consider the distance for all the data points at the same time, and somehow get the overall distance as close to zero as possible. To achieve that goal, we can start by using this equation. Yi is the exam score of student I, B0 is the intercept of the red line, B1 is the slope of the red line, and Xi represents the hours that student I spent studying for the exam. So hopefully it's clear that this portion represents the red line. This portion gives you the red line if you plug in for different values of X. And finally, we have the last term Mi, and I'm going to call it the prediction mistake for student I. So for student I, you can think of Mi as the vertical distance between the data point and the red line. Mi can be 0 or positive or negative because Mi equals Yi minus a point on the red line for student I. So for student I, if the score or Yi is above the red line, then Mi or prediction mistake is going to be positive. And if the score is below the red line, then Mi is going to be some negative number. So that's what this equation is. It simply expresses the exam score in terms of a point on the red line and the prediction mistake. As an example, if we look at this particular data point, the exam score for that student can be expressed with this equation, which says that 0.8, the exam score, equals intercept plus slope of the line times 5.8, where 5.8 is the hours studied for this particular student. And of course, we have to consider M7 as well, which is the prediction mistake for this particular student. The 7 in the M is just saying that this data point corresponds to student number 7 in our data. If the number 7 is confusing you, you can simply think about student number 7 as a student with a particular name, for example, Chris. And student number 1 could be Jeffrey, and student number 2 could be Ashley, for example, and so on and so forth. Now, coming back to student number 7, the M7 or the prediction mistake represents the vertical distance of this line. And it's going to be positive for this student because the score is above the red line. For another student, student number 10, the prediction mistake is negative because the score is below the red line. For student number 16 in our data, prediction mistake is also going to be some negative number. So across the data points, we're going to have a mix of positive and negative numbers for M, or prediction mistakes. And prediction mistakes are important because, as I explained already, the general goal is to fit a line through the data points such that the vertical distances between the data points and the fitted line is as close to zero as possible. Now, to achieve our goal, what we're going to do is we're going to minimize the sum of square vertical distances or squared prediction mistakes. In other words, we're first going to square all the prediction mistakes one by one, 1 through 30, because we have 30 students or observations in our data. And then we're going to add all the squared terms, all the squared prediction mistakes. The goal is to find the line that results in minimum value of sum of squared prediction mistakes. And this makes sense intuitively because if we square the prediction mistakes, then we'll get all non-negative numbers. And if we add all of those numbers, the resulting sum is one way to represent the overall distance between the line and the data points. So then now we can state our goal a bit more mathematically. And that is to fit a line or find a line through the data points such that the sum of square prediction mistakes is minimized. And this goal is the same as the goal where we solve for B0, intercept of the fitter line, and B1, slope of the fitter line, such that the sum of square prediction mistakes is minimized. So then how do we actually find the fitter line that achieves our goal? How do we carry out the calculation? Well, that's for part 2. In our next video, part 2 will cover solving for B0 and B1 of a fitter line that minimize the sum of square prediction mistakes. And then we're going to talk about the results.